So for those who don't know Christian, he's a graduate of universities in Austria, Technical University of Vienna and University of Vienna, where he did his first degrees in chemistry, physics, and astronomy before, in the early 1980s, before going on to finish his PhD in astronomy and chemistry at the University of Graz in Austria in '83. And then he did his habilitation, which is a German-based system at the University of Vienna in geochemistry and cosmochemistry. He has traveled widely and been visiting scientists in many places. He had a Fulbright fellowship to NASA in 1988 to 1991, and then visited Carnegie. He was here several times at Wits, Dartmouth College in the US, as well as the Open University in the UK. And in 2008 to 2010, he was the head of department at the Department of Lithospheric Research at the University of Vienna, before going to his directorship at the Natural History Museum in Vienna from 2010 to 2020. He has just had a big retirement party that was a surprise to him, so you can't surprise old people, but he is still associated, obviously, with University of Vienna and will continue to be. He's the author or co-author of 23, or editor of 23 books, has produced over 500 publications. I didn't try and get the up-to-date number, because if you go a week early, then Christian's got more. So over 500 publications. He has led many international expeditions, mainly looking at impact craters, international drilling projects around the world, and has organized more than 24 conferences in his time. So he's a real ball of energy, and so on. He's here at the moment because people may know the ICDP committee is meeting in Johannesburg, and he is a member of that. He also currently chairs the Scientific Advisory Committee for the Barringer Cratering Company, which is a major benefactor of impact research in the world. So, Christian, thank you for taking time to be here. I hope you are suitably recovered after your travels, and we look forward to your talk, which has wide-ranging implications for us all. Thanks.
Thank you, Roger. Thank you for the introduction. Thank you for the invitation. It's amazing being back here after quite a number of years. Between the late 1980s and the mid-2000s, I used to come here about once a year, and we did a lot of work on impact craters in Southern Africa and related topics. As Roger mentioned, I'm here actually this week because we just finished the ICDP, the International Continental Scientific Drilling Program Executive Committee meeting, of which I'm the Austrian representative. I've been involved in drilling projects around the world over several decades. We drilled a number of impact craters around the world, including Bosumtwi in Ghana, Chesapeake Bay in the United States, Chicxulub in Mexico, and El Gigitkin in Russia, and a few other things. So, in fact, however, it is a little bit silly that the meeting was here exactly this week, because exactly the same week, this week, I should have actually been in Stellenbosch, because there the International Planetary Defense Conference was taking place, and I was on the organizing committee of that particular meeting as well. So, but since I'm on official kind of mission here for the ICDP, I had to go to that one first. And but I'll tell you a little bit about what's going on in the topic of planetary defense. So let me start here by showing you a comparison between the surface of the Earth and the surface of the Moon. And this is how they kind of currently look like. And you might wonder, why are they so different? Why is the Moon covered in impact craters? And as a side note, I have to specify, we really only know that these craters are of impact origin, more or less really since the first lunar missions, the Apollo missions, and brought back samples and confirmed the impact origin of a lot of these things. Suspicion was already starting in the early 20th century, but since the time when craters on the Moon were discovered in the 1700s, Until the beginning of the 20th century, people mostly thought they were volcanic in origin. But now we know they're all impact craters. But so, okay, so the lunar surface is covered in impact craters. You don't see anything like that on the Earth. Well, of course, the blue planet has a lot of water, and it has clouds, and it has an atmosphere that screens out some of the smaller bodies that can make impact craters, but not the big ones. So why don't we see them? Well, the obvious answer is because the Earth has a lot of active geological processes going on that obscure impacts that actually do happen. So if you want to know how many impacts have happened on the surface of the Earth, look at the lower part of the image. This is how the Earth would look like if it hadn't been erasing and obscuring the impact record since the formation of those craters. However, on the Moon, even small bodies make craters, impact craters, because the atmosphere doesn't screen out even the small ones, and there are no active geological processes going on, kind of altering the surface since then. So the lunar surface really is covered with big and small craters back and forth. Before we kind of come back to the Earth, I want to show you a couple of images of other bodies in the solar system. Here we have representatives of the inner planets. On the upper left, we see Mercury, the surface of Mercury. This is a photo mosaic from one of the spacecraft. It shows a surface that looks very much like the Moon. It also doesn't have an atmosphere. Geological processes have been rather limited since the last several billion years. So we have craters, 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 craters. On the upper right, we see the red planet, Mars. And again, at least in this particular image, it is dominated by impact features, impact craters, large and small. What we see here mostly is the southern hemisphere of Mars, which is dominated by impact structures. The northern part, there have been some changes. There's volcanic features as well, but still lots of impact craters. Mars has a very thin atmosphere, which is a little around the 100th or so of the Earth atmosphere, and it is smaller, of course, but still. And what we see on the bottom is a radar image of a crater on the surface of the planet Venus. Venus is known as the sister planet of the Earth in the solar system. It is almost as large as the Earth, not quite, a few hundred kilometers are missing, but still. And it has a very dense atmosphere, which is about 100 times denser than the Earth's atmosphere. So small bodies don't make it through. Craters on Venus start at several kilometers in diameter, and therefore, because of the atmosphere also, we do need radar images. So that's why you see that particular image here. You see the crater and its ejecta very well. The crater is the nice, let me try to delineate it here with the mouse. So this is the crater actually, and there's a central uplift here. And what we see around here is the material that was thrown out during the impact. Because of the dense atmosphere of Venus, it doesn't fly very far. It is contained by the atmosphere. On the Mars or Moon, it would fly much, much further, and also on the Earth. So the inner planets, of which there is Mercury, Venus, Earth, and Mars, at least 3 of them, impact craters are fairly obvious. On the Earth, not quite so much. On Mars, by the way, because we have spacecraft orbiting Mars, we can actually follow the formation of new impact craters all the time. So what we see here is a small impact feature. This one in here, and the bluish stuff are ejecta that was appearing in an image that was taken in the year 2011. A comparison image of the year 2009 didn't show anything. So that's a new crater that formed. On the Moon, actually, there have also been several impact craters seen kind of in formation, so to say. So here are, I'll come back to that a little bit later, the bodies that are more or less responsible for all these impacts, which in the solar system is the asteroid belt, which is mostly between the planets Mars, the inner planets, and Jupiter, the outer planets. And this is the remnant material, the leftover material from the time of the origin of the solar system 4.5 billion years ago. And those are the asteroids or minor planets. And you see here a few images collected of asteroids that had already been visited by spacecraft. And there's at least two things that are interesting to note here. The first one is that they all have irregular shapes because they were not large enough to gravitationally settle into a round body shape. And the second thing we notice is that even those bodies that range here in size of a few kilometers up to a little over 100 kilometers, they all are covered by impact craters themselves. So collisions are common between those minor bodies, of which there are, by the way, millions out there. And I'll come back to that point later. So this is where the material kind of comes from that then impacts on the Earth, on the Moon, on Mars, and so on. Now let's go back to the Earth. And here is one of the iconic craters on Earth. That would be a meteor crater, or also called Barringer crater. Roger already mentioned that name. This is a particularly important feature for us impact researchers. It has a diameter of about 1.2 kilometers. It's about 250 meters deep. And its discovery or investigation history in the beginning of the 20th century by a researcher, or actually he was an economic geologist, more like an impact person, because impacts were not known at that time, named Daniel Moreau Barringer. At the beginning of the 20th century, his work set the stage for modern impact research. And I'll tell you why. This feature was discovered, of course, known to the native people for a long time, but noted by scientists, I would say, in the late 19th century, because there were meteorite fragments found around that crater, iron meteorite fragments. And they were studied by people on the East Coast in the museums. And there was some researchers that went there and thought, maybe that crater was formed by a big meteorite and made that crater. And those are fragments and so on. But somehow that connection was not established. People thought, no, it was probably an explosion feature, something related to volcanic outgassing or something like that. And interesting enough, the meteorites that were found kind of around the crater here were named after that feature back in the upper right corner here, which is called Canyon Diablo. So if you ever see Canyon Diablo meteorites in any museum, that's where they came from. And they were not called after the crater, which by the time, of course, was not called Meteor Crater, because nobody knew that it was one of those. It had the funny name Coon Butte, because there were these coons sitting around out there sunning themselves. And so they had that was the name. But then Barringer kind of heard about it, and he was convinced that, in fact, there was a big meteorite buried underneath the crater floor, and it would just be excavated. And of course, an iron meteorite contains a lot of rare metals like nickel and cobalt and platinum group elements and so on. So he wanted to mine that out and get rich. So he got the land rights to that crater and started drilling and digging and found nothing. The only thing he found, that there was brecciated rock underneath the crater floor and no big meteorite. And at that time, there was kind of, okay, so why is that? People didn't understand that very well. And here's an interesting little side story of, well, what should I say, about how science develops on the one hand, and also that publications matter. So what was not known really at the time was how do large extraterrestrial bodies that hit the Earth really interact with the surface of the Earth. And what people didn't consider earlier on was the enormously high velocity with which these bodies impact the surface of the Earth or the Moon. And this is why also people didn't realize that the craters on the moon are of impact origin. And well, those of you who remember physics may remember a very simple equation for kinetic energy, which is 1/2 times the mass times the velocity squared. So if we have a high velocity, the kinetic energy that is being released upon impact is enormously high. And that concept for the first time was written down by an Estonian postdoc, just finished his PhD, named Ernst Öpik. And he published that thought, these calculations, in a Russian amateur astronomy journal in Russian with a French abstract. In 1916. Okay, so an unknown person publishing in an unknown journal in a language that hardly anybody understood and so on, you can imagine. Nobody took notice of that. But his main conclusion was, we don't need a big body to make a big crater. A small body is good enough, because when that hits the surface of the Earth, it kind of explodes and makes a huge crater. And the relationship is about 1 to 10 to 1 to 20 for the impacting body to the crater. Well, 3 years later, there was a young physicist from America, Herbert Ives, who had been in World War I, and he had noticed that when grenades hit the sand at the beach in Normandy, they would explode and make a big crater. And the grenades were relatively small in comparison. And so he published a paper in the, at that time, relatively new astrophysical journal about that energy relationship of a small body making a big crater, and that would explain that the craters on the moon are of impact origin. Well, because he had no record in publishing, and that was an outrageous idea to most of the people at the time, and of course establishment people were criticizing it, his work was ignored. It was only in 1924-25 when, and it's kind of in a way sad, a proper astronomer, an old guy with a white beard, at an observatory in New Zealand, who was a well-known institution, published the same story more or less again, but without knowing the other works. So he reinvented the same thing the third time. In the publications of that particular observatory that were well read among the researchers, that finally people took notice. Aha, you need a small body, make a big crater. So then the advisor to Barringer told him, maybe there is no big meteorite under the crater floor, because it exploded, and what we have left over, the few percent, that's all there is left, because the rest vaporized. Well, that was not exactly what Barringer wanted to hear at the time, because he had spent 20 years of his life and a lot of money drilling and digging around there, and then at the end, there is nothing. So his original idea was right. It was an impact crater, but there was no meteorite left. So that was what kind of was learned in the beginning of the 20th century on that crater, why it is so important. Barringer, however, died 2 years later of a heart attack, relatively young, and rather disappointed. His family still has the rights, the land rights there, established a museum. Now the tourists are being mined, and the family is actually a great benefactor to impact research, and I happen to be chairing their scientific advisory committee. So anyway, it's always nice to kind of be there and talk back. But this crater really had a great importance in impact crater research. Now, let me bring you to some place closer to here, especially the one image on the bottom here, Zweig, not very far from here. Please notice the diameter is the same, 1.2 kilometers, as the Barringer crater that I just showed you. And it took a long time to establish, and I was involved in that. We finally published some papers in the early 90s, that this is actually an impact crater, because there is no rock on the surface that would indicate that this is an impact crater. We had to drill down about 100 meters to find rocks that show evidence of the impact. And so what we have here is a lake, and lake sediments that fill in that particular crater. And if you look also carefully here, it's not so easy to determine the crater rim. It is not all that sharp. Let's just go back to that one here. Nice, sharp crater rim. Clearly visible. Here, not so much. What's the difference? Diameter is the same. The difference is meteor crater or barrier crater formed about 50,000 years ago. This one here about 250,000 years ago. Now, geologically speaking, that's almost no big difference, but that is enough to already start obscuring an impact feature. And that tells you how fast impact craters on the surface of the Earth are disappearing. The one in the upper left is also one that's not very far from here. We also worked there for some time in the 80s and 90s, Rotterdam. And you barely see any rocks of the crater rim that are still sticking out through the sand. And the whole area is covered by sand. We did a lot of GPR to look where there might be some impact deposits, and then dug down there and so on, found some stuff. Also not so easy. And you know that one, of course, one of the oldest impact structures on Earth, and the largest known, in fact. But what we see here is not a 300-kilometer diameter feature. That is the reconstructed diameter, because what we see here, this arc, is about 70 kilometers in diameter, and that is only the remnant, the very deeply eroded remnant of the central uplift. And the original crater structure has been eroded away because we have lost, since formation about 2 billion years ago, from the surface through erosion down about 10 kilometers plus minus. So what we see here used to be, after the impact, 10 kilometers below the surface. So if you have a small feature like one of those that is only a few hundred meters deep, they are gone after a few million years. They are eroded away from the surface of our planet. And that is a little bit of a problem when we want to identify craters on Earth. And so we can't rely only on circular features. And the problem is that most circular features on Earth are not impact craters, because there is many other geological processes that can form circular features. And I won't go through many details, but only a small percentage of circular features may have an impact origin on Earth, not on the Moon, different. So it took many, many decades of study and the development of criteria to identify, or to help us properly identify impact structures, especially those that are hardly preserved or only partly preserved, or where we only have some drill core samples, et cetera, et cetera. And I don't have time today to go into those details. Suffice to say that what we really need is, it's not good enough to do remote studies. So a photograph of some circular feature, I call it the curse of Google Earth, because people constantly send me pictures and say, I found a new impact crater. Well, and how the rocks like, you know? Did you look at the geology? What's the mineralogy? No, nothing, not that. A round feature. No? That's not good enough, you know? And so what we need is to actually look at the rocks to see if there is evidence of what we call shock metamorphism. Because if one of those extraterrestrial bodies hits the surface of the Earth with these enormous velocities, there are many kilometers per second. So we have extremely high shock pressures released on a very short time scale, and we're talking about many gigapascals. And so this is much higher than any normal indigenous geological process would allow. So we have evidence for that shock features, or we have contamination with extraterrestrial material, which takes very sophisticated and detailed geochemical analysis to find those. And these kind of studies have led to the identification of currently around 200 impact craters on Earth. About 2/3 of those, there is some part visible on the surface of the Earth. For about 1/3, not. You actually have to drill down. You find these things maybe from geophysical anomalies, and then you have to drill and look at the drill cores. So about 1/3 of those craters are not even exposed on the surface of the Earth. Another thing you might notice is that they are not exactly regularly distributed across the surface of the Earth. There are some areas that have more than others. For example, Southern Africa, Australia, Northern Europe, and Northern North America. And that has to do with the age of the rock units there. So the older rocks, of course, preserve older craters as well, whereas it's also very difficult to see them in the middle of the jungle, and they won't necessarily be preserved there, also in areas where you have a lot of tectonics going on. And not much on the ocean floor, because the ocean floor is generally very, very young compared to the rest of the surface of the Earth. But again, this is not the topic of today's talk. So what do we have on Earth in terms of impact craters? The oldest impacts the oldest impact craters that are preserved would be Yarrabuba in Australia and Vredefort here in South Africa, about 2 billion years old. Well, the Earth is 4.5 billion years old, so what do we have for the first 2.5 billion? Well, there are some impact ejecta layers, spheral layers, in the age range of about 3.4 to 2.5 billion years age. The craters themselves have not been found, probably long eroded away, but some ejecta patches are still left. So the early impact record on Earth is not that well documented, also because the rock record that is that old is very limited on Earth as well. Then the next billion, so between about 2 and 1 billion, is also not much preserved. And most of the craters we have are younger than a few 100 million years. Clearly understandable, as I said, because especially the small ones will all be eroded away. A very famous case of an impact, and it took a long time also to figure that one out, is the so-called Cretaceous Tertiary, or now called Cretaceous Paleogene boundary, which is marked by, as everybody knows, the extinction of the dinosaurs and many other fauna and flora at the time. Here is a photograph of the boundary between the Cretaceous rocks and the Tertiary rocks at a place in central Italy. And it was nearby in that area where researchers in the late 1970s were studying these rocks. And they were actually looking for something totally different. They had tectonic questions, but they also analyzed some trace elements in these rocks, and also included that thin layer in here that is, you see kind of a brownish layer in between those rocks. And that was included. Then they found, oops, this is very, very rich in platinum group elements, very unusual. And the ratio, the elemental ratios of these platinum group elements are looking like a meteorite, an extraterrestrial body. And their abundance is 100,000 times higher than the crustal abundance. So impossible to come from normal crustal procedures because nothing else shows any anomaly. So this was published in 1980. That's the famous Alvarez paper that explained that there was an asteroid impact at the Cretaceous Tertiary boundary. And of course, the general geology community was immediately skeptical, of course, as usual, because nobody had heard about impacts much before. It was just not talked about in the geological community because a few specialists, especially researchers that also worked on lunar rocks and things like that, they knew about impacts, but the normal geologists had never heard about that or learned about that. So it was at the time when I was also just starting my work, and I was at many of the conferences in the 1980s, and there were vigorous debates going on, and sometimes vicious debates. And I remember a paper published by a historian who said the acceptance of the impact hypothesis was directly proportional to people being familiar with impact processes, such as those people having worked on lunar samples. So paleontologists had never heard about an impact before. A lot of geochemists and mineralogists said, of course, makes sense, you know. So it was a difference in the communities as well. So anyway, it also didn't help that nobody found an impact crater that was fitting. And it took another 10 years before a candidate was found and finally confirmed to be the impact crater that is associated with the Cretaceous Tertiary boundary. And that is an artistic impression here of the impact. And what was found was a 200-kilometer diameter crater covered by about 1 kilometer of younger rocks. That's why they didn't find it, because it was not exposed on the surface, on the Yucatan Peninsula in Mexico. And by now it's established, has been drilled many times, including by projects with the ICDP and so on, and hundreds or thousands of people around the world have been working on it. So, but more important for the topic, I still have, about 15, 20 minutes left here, that we're talking about today here is, what kind of effects do impacts like that have? Well, we have, depending on the time scale, we have, first of all, the fireball, of course. There is a thermal pulse from the ejecta, because these hot melts are thrown around from impact that size. They're thrown around for many, even tens of thousands of kilometers from the impact site. And they would set, at that time, there was dense woods. They would set many areas on fire. We could still find in the geological record the soot from the fires of that particular impact event, and even tell you from the isotope composition what exactly burned. We had, of course, gigantic tsunamis and winds, and they call them hypercanes because hurricanes are not good enough to explain something like that. And then, because of the large amount of material that was thrown out, and a 200-kilometer diameter crater that initially was down about to 60 kilometers below the surface, that's a lot of material. And so if you calculate how much dust was thrown in the atmosphere, we're talking about several tens of thousands of cubic kilometers of dust. That's a lot. And that obscured the sunlight all around the planet for years, which meant hardly any sunlight on the surface, no plants growing for a while, animals that eat plants die of hunger, animals that eat animals die because there's nothing there. So food chains collapse, and that was a major reason of the extinctions, besides poisoning from all kinds of stuff that was thrown out there. Acid rain, for example, then the ozone layer was destroyed, nitric acid went down, sulfuric acid, and so on and so forth. So that caused what was also called an impact winter, in analogy to a nuclear winter. So it was cold for some time. Then, after some decades, it started warming up because a lot of greenhouse gases were thrown into the atmosphere from the carbon dioxide to the water, and that increased the temperature afterwards for a while. If there was any impact-triggered volcanism, it's still a question of debate. We don't know for sure. But there certainly was disrupted climate. Apart from, of course, you can imagine that within several crater diameters of the impact itself, because of the destruction, there was no living thing left anyway. And that kind of brings us to the point, what happens when you have these large impacts? What is the effect on life? So we know that even 4.5 billion years ago, the Earth, this is how it might have looked like a little over 4 billion years ago. There was a surface ocean. The moon was much closer. Impacts happened. And today, impacts happen. And some of the older ones of us remember in the mid-1990s, there was a big event, Comet Shoemaker-Levy 9 on Jupiter, where a comet was breaking apart due to the gravitational interaction with Jupiter. And it was breaking into about kilometer-sized chunks. And one after the other was going on Jupiter. So this was what happened on Jupiter, what is left on Jupiter. Jupiter doesn't have a solid surface, but a dense atmosphere. And so a body about a kilometer in diameter makes an impact scar. It disappears after a few months on the atmosphere of Jupiter. And because Jupiter is much larger than the Earth, it is also valuable to compare the size here to the size of the Earth. So a kilometer-sized object makes a scar, so to say, quite big in size. That shows you the effects, basically, the impact effects, how far they go. So how often do impacts occur on Earth of various sizes? So, meteor crater in Arizona, which we've seen, a crater of this size is formed on Earth every few thousand years. Now, this curve is constructed based on observed impacts on the Earth and the Moon. Then we have, I'm sure some of you may have heard of Bosumtwi in Ghana. I know at least somebody who was there. It's about a 10, 11 kilometer diameter impact crater. And that forms maybe every few 100,000 years, maybe every million years, something like that. A little bit larger, Ries, 20-something kilometers in diameter, southern Germany, about every million, 2-3 million years. And Chicxulub, the one that killed the dinosaurs, maybe every 100 million years or more, something like that on Earth. So you can say the larger, the less common, the smaller, the more often. And on the bottom, sorry, it's in German, it tells you the diameter of the asteroid or comet body that hits the Earth. So for something like, and I haven't said that really yet, something like meteor crater, the object, that iron meteorite that caused that 1 kilometer diameter crater was only about 50 or 60 meters in diameter. So the size of a big house, big building. Makes a crater that is quite big. The Chicxulub one, the 200 kilometer diameter crater, about 10, 12 kilometers in diameter. So we have that ratio of about 1 to 20, 1 to 15, something like that. So that means a small object has big effects. Now, where do these things come from? We're going back to the asteroids now that I showed you a few images earlier. And this shows you the orbits of Mercury, Venus, Earth, and Mars, and the orbits of Earth-crossing asteroids. Those that get close to or can cross the Earth orbit. And you can't even distinguish the individual orbits. There are so many of those. But I'm only showing you the ones that are larger than a kilometer in diameter. Let that sink in for a moment. Okay. But smaller objects also interact with the Earth in the Earth atmosphere. Some of you may remember in the news a little over 10 years ago, in the morning, Chelyabinsk in Russia, there was a big explosion in the atmosphere, and the pressure wave from the explosion that happened a little over 20 kilometers altitude caused a lot of damage in a city called Chelyabinsk that was over 60 kilometers from the explosion point in the atmosphere away. In the middle images, you see broken down windows, knocked down walls, and so on. And what was that? That was a body about 20 meters in diameter that exploded in the atmosphere. It didn't even reach the surface of the Earth. Because of the internal fractures, it just broke up and exploded, and it was not the impact pressure, it was just basically the pressure wave from the explosion that caused all this damage. About 1,500 people had to go to the hospital because they were injured from that. If that explosion would have been closer over the city, there truly would have been hundreds, if not thousands of people dead. And what was that? It was interesting because for the same day, the close passage of a small asteroid was predicted. And in that image, here's the Earth. And here's that green line of a small asteroid with the interesting number 2012 DA14. And people thought, well, astronomers got it wrong. That was, in fact, that body, but that was supposed to come in the afternoon. The other one came in the morning. Turned out it was a totally different body, came from a different direction. Here it is, that red one, and it hit the Earth. So, on that particular morning, 3 bodies happened to be in the same place in space here. Earth, and one very close to Earth, and one that just hit the Earth. and all these others were relatively small objects. So these explosions in the atmosphere, they happen all the time, in fact. And there are what are somewhat funnily called US government sensors, spy satellites and stuff like that, right? But they are supposed to monitor possible nuclear explosions. But they also see the explosions that come from outer space, so to say. And here is a map that shows all the explosions in the atmosphere between, say, 1988 and 2024 record. That's quite a bit. And the blue and green ones are small ones, higher up. And orangey and yellow ones are bigger and lower down. And the big orange one up here, that's Chelyabinsk. That was the largest one in that time period. Well, but you see many others. Yeah, an interesting point of comparison to the impact crater map is here, these things are uniformly distributed over the Earth. So it's not the same effect. So the bodies coming from outer space, they come from all directions. No continent and no area is preferred, no direction is preferred. Whereas the craters that we see that are preserved, there's geological reasons why we see these preservations where they are, okay? Okay, so this happens all the time. By the way, there's a question that often comes up, and I'll just preempt it. When people ask me often after a talk like this, so when an asteroid like this hits the Earth, doesn't that knock the Earth out of its orbit? Think about driving in a car on a freeway and you have a bug splashing on your windshield. Does that knock your car out of driving? No, it doesn't. And because the bug is so much smaller in mass than the car. Actually, the ratio between the Earth mass and the mass of a small asteroid is even worse in such a case. So it doesn't do anything to the Earth orbit. So to say that in advance. Now, in 1908, there was a bigger version of Chelyabinsk going on in Russia, Tunguskad's famous place. It was a 50-meter object exploded, and it flattened an area about 2,000 square kilometers of trees in the explosion wave. So to commemorate that, the UN has designated in 2016, the 30th of June, the anniversary day, is the Asteroid Day, and there have been events all over the world, in planetariums and observatories and other places, commemorating that and telling people about the dangers of impacts. And we have these, as I mentioned at the beginning, planetary defense conferences going on for a while now, and they often include an impact exercise. The exercise is a hypothetical impact. Let's say people are discovering that there's an asteroid in collision course with the Earth. So once that object is discovered, we don't know very much yet because we don't have the orbit of that object very well defined yet. We don't have the mass, the size, etc. Takes a while, takes more observations. So if you take the first kind of discoveries, you have this huge area here where it could impact. A few weeks later and more observations, it kind of narrows it down to a much smaller area. So here you have, this is Europe. You see here this area, there's my home country, Austria. Next to this, the Czech Republic, there's Germany. And so we end up finally with this impact somewhere at the border between these three countries. But originally, it could have happened anywhere from Northern Africa to the Arctic. So, and these are exercises that scientists go through kind of to know what has to be done when a potentially dangerous object is discovered. What observations do we need? How long does it take to refine it all? And so on. So also not totally, you find it occasionally in the news, there's an object called Apophis, and for a long time it was in the news that it might actually collide with the Earth in 2029 or in 2036. And so it has a diameter of about 375 meters, so that's quite a big object. It's a stony asteroid. And observations very recently confirmed, in fact, it will miss the Earth. So, at least we hope so. So as I said, discovered in 2004, it was identified as one of the most hazardous asteroids that could impact the Earth in the near future, in the next 10, 20 years. So now finally, they are pretty sure it will bypass the Earth in 2029 and also in 36, maybe 2068, but the indications are also not very good for that. However, if that would have been if there would have been an impact, it would have made a crater about, what is that? That's about 5 kilometers in diameter. And explosion region about, what's that, 3,000 square mile, 2,000 square miles. I don't know how much that is in square kilometers. Yeah, whatever. But it would have been 1.2 million kilotons of kinetic energy as compared to 15 kilotons of the Hiroshima atomic bomb explosion. So we're talking about quite some effect. So this is I'll skip that because that just shows the observation, so it will bypass the Earth. This is in comparison. How big is that asteroid? Well, compared to 2 big cities with skyscrapers, pretty big. And this is, if it would hit Manhattan, Manhattan wouldn't exist anymore afterwards, and the surroundings wouldn't look very good either. So that's one asteroid. How many others are there? This is an interesting diagram. Now, I said there's millions of asteroids in the asteroid belt, but how many are there that are actually coming close to the Earth? If you would have asked that question 20 years ago or so, let's say around 2000, the astronomers would have said, well, maybe about 1,500, 2,000 of those. And since that time, people have been doing discovery programs with telescopes, including space telescopes, looking how many are there. Guess what? Every year they found more and more and more and more and more. The ones that are bigger than 140 meters are now at 10,000. That's 2022 here, by the way. And all together, including smaller ones, including those that make, let's say, meteor crater-sized craters and stuff like that, or Tunguska-sized explosions that flatten average cities, stuff like that. A side comment, by the way. In 1908, why weren't there any dead people at the time of Tunguska? Because it was an uninhabited area. Because at that time, the general population on Earth was less than 1 billion people. Now we're at over 8 billion, and there is hardly any uninhabited place on the Earth anymore. So if the impact happens anywhere now, or the explosion in the atmosphere, you know what's happening. Anyway, even the smaller ones are now close to 30,000. Okay, that was, as I said, 2022. Fast forward to 2 years, 2024. Where are we now? That's still almost a year ago. Close to 36,000 and 11,000, 12,000 for the 140. So every year we discover more and more and more. And that curve doesn't show us if it's kind of flattening yet. So the search programs continue to find more and more potentially dangerous asteroids out there. What can we do if one is discovered that might impact the Earth? Well, here the answer would be, depends how much time we have. If we only have a few weeks or maybe a couple of months, all you can do is try to calculate where the impact might happen and try to evacuate people. And good luck with that, because you know what happens when there are hurricane warnings and other things. If you have a few years, then there's something that can probably be done. And that is, say, nudging the asteroid and kind of giving it a slight bump to change its orbit a little bit so it misses the Earth. And to test that concept, in 2022, NASA impacted a spacecraft on the moon or small moon of an asteroid. It was called the DART mission, the Double Asteroid Redirection Test. So darts, throwing darts. And it hit that particular asteroid called Dimorphos, small, several hundred and something meters in diameter. And The original orbit is shown in white, and the new orbit afterwards shown in blue. So it actually did change the orbit around that main asteroid. So it was possible with the impact of a body that was not even weighing a ton, but was going at full speed into that small asteroid, to actually give it a nudge. And it would have been enough if that had been on an Earth approaching orbit, but we had, again, several years before, yeah? Then it would fly by. If you have less than that time, then even sending Bruce Willis up there won't help, you know? So it's, anyway, and now there's a Hera mission, a European Space Agency mission, that is going to fly there now to check out the damage. How does the crater look like from that impact of that spacecraft and so on? So what can we kind of learn? How did the asteroid react? Because it depends also on the internal structure and the composition of that asteroid, how it would react. So there's a lot to be learned. Those are the first attempts, the first spacecraft that tried this out. So there is a chance to do something, and we're just now starting to work on these things. There are, as I said, just some conferences on this topic. There's a United Nations affiliated group of researchers that works on these problems. And this group has been meeting over the last few years. They're in Vienna. In fact, Vienna is one of the United Nations headquarters. We have the United Nations Office of Outer Space Affairs in Vienna. And affiliated with that group, there's an international group of researchers, of which I'm a member too. And we've been meeting, and we've been basically declaring that in 2029, the asteroid Apophis comes close to the Earth. The event has the potential also to increase public understanding of the risk and so on. And there was a proposal to designate 2029 as the International Year of, it's been changed slightly, of asteroid awareness and planetary defense. And that particular proposal has just a few months ago been approved by the General Assembly of the UN. So 2029 is now designed the International Year of Asteroid Awareness and Planetary Defense. And that will provide an opportunity for those of us active in the field to go out there and educate people and hopefully raise awareness. And also more studies will be done, more research about how to possibly defend us from this. You know, it's a national hazard. It should not be overestimated. There's still earthquakes and weather events and all kinds of other things. An earthquake can't be predicted. Asteroid impacts can, to some degree, be predicted. And let's do something about it if we can. And with that, thank you very much for your attention.
Thanks very much, Christian. I know students might have practicals and things to go to, so if you need to leave, we do understand. And Robin, you've got people online. There might be questions online. Okay, so we have a question.
Okay, sir, nice presentation. You mentioned something very interesting that I wasn't actually aware about when you were talking about the impact that hit Russia in 2013. You said that the meteor exploded. What I know is that when they enter the Earth's atmosphere, they break down from the surface inwards, so they become smaller. So now you said that it exploded. I wasn't aware. I didn't know that actually happened. So what my question is then, how does that happen? What's happening in the core of the meteor?
Right. Okay. What you're thinking about or probably heard about is smaller objects. That is meteor-sized objects or even smaller than that, which are what we see in the atmosphere as a meteor or a fireball. Very often goes through there. And those are effects where you have a small object, maybe say this size, and it enters the Earth's atmosphere at high velocity, and it causes the friction heating of the atmosphere, is what we see. And the object itself is melting away a little bit or breaking up, and that's small objects. And it might be something left over, and then it falls on Earth when it's slowed down as a meteorite. If you have an object that is bigger than usually a few meters to a few tens of meters in diameter, it is possible, but not always the case, that they have fractures. And in these fractures, as they enter the atmosphere at high speed, it is actually possible that atmosphere enters and then at one point, because of the high temperature, kind of blows it up from the inside. And that's what is happening in these larger, the effects are called air bursts. And then you have still some small fragments that come down. In the case of Chelyabinsk, there were some small objects that were left. But the main thing exploded there in the atmosphere. It's not said that everyone does that, but some of them do that. Tunguska did it, Chelyabinsk did it, some others do it as well.
So, just remember that that object was probably the product of another impact, which is why it's fractured.
Fractured inside, yeah.
So the stony ones come and they break.
Iron meteorites don't do that stuff. Okay.
Scott?
Yeah, I was just going to ask, I mean, if we think that like a KT boundary type of sized like impactor, right, is colliding every 100 million years or so, wouldn't we expect to see more geological evidence of large, like there should, we should find lots of like, large numbers of like spherical layers or like, paleontolomites or that type of thing.
Well,
stratigraphy.
Yeah. Well, it depends where the impact happens. And considering that the Earth's surface is covered to about 2/3 with ocean, if you have an impact in the ocean, then first of all, the effect will be different if it hits, say, basalt, boring basalt, as if in this case it hit a mixture of carbonates and sulfates and a thin layer of water that went up in the atmosphere. So it depends on the effects what comes out of it. Then, of course, if it happens in water, the top part of your energy production consumption goes into vaporizing the water. And the crater on the ocean floor will be smaller, even though you have a 10, 12 kilometer diameter asteroid, something like that. So the effects will be less, and the material won't go as far. And even if it did, at that time, the ocean floor from 500 million years ago has been recycled 3 times in the meantime already. So we do have impact ejecta from going back, but yeah, not that huge amount for considering. But also if you go back further in time, how many of these actual spheral layers, the Archean times, do we have? A handful, half a dozen, a dozen, and that covers 1.5 billion years. So the preservation rate is very low.
We live in hope.
A couple of questions. One is, these discoveries of near-Earth asteroids that are just increasing, does that have any impact on the estimates of how many asteroids are actually in the asteroid belt, or is that based on independent considerations? The other question I have is, like, how frequent are comets compared to these asteroid impacts? Or
Okay.
is it actually lesser?
Right. Okay, so first, how many asteroids are there? More and more and more. But it's not that we're discovering more. And if you would have looked at how many asteroids were in the list at the beginning of the 20th century, you would have found a couple of thousand. If you looked later in the 20th century, 10,000, 100,000, 1 million. And now we're at least 2 million, something like that. It's kind of the closer you look, the more you find, because you get the smaller and smaller and smaller ones. Earlier on, we saw only the ones that were big or the ones that came close by Earth. So there is a lot of stuff out there, but we don't know it all yet. When I finished my studies in astronomy, which was in 1983, not a single exoplanet was known. Not a single Kuiper Belt object was known. They all were discovered, starting to discover them, the first ones in the 1990s. Yeah, so now we have thousands of exoplanets and thousands or tens of thousands of Kuiper Belt objects. So, you keep looking, you keep finding stuff. Comets are much rarer. Comets come from the outer solar system. They're big chunks, mainly of ice, with a little bit of rock and dust mixed in. And they are in orbits between the planets, usually very long elliptical orbits. And the chances of a comet hitting a planet are much smaller than that of asteroids, simply because there are fewer of them. It's like the same thing. how many 10-kilometer size asteroids will hit the Earth, how many 10-kilometer size comets will hit the Earth, about a tenth of the number of the asteroids for comets, and smaller ones hardly any. So some small objects, a lot of dust drains down that way, because that is when the comets get close to the sun, they're kind of fragmenting, and since it's mainly ice, it's the dust that's left over, and that accumulates. We accumulate 40,000 tons of dust every year, extraterrestrial dust every year on Earth, so, and a lot of that is cometary.
Okay. Did you have a follow-up question?
No, it's a different question.
Okay. Let's just do everyone's. So you had a question in front.
Thanks, Christian, for a nice
Yeah.
presentation. I like it quite a lot. My question relates to those glass objects that we found, like the Moldavines, for example. Does every stone meteorite produce it, and what are the parameters for a meteorite to produce that glass?
That's a rather special question. I didn't talk about any glasses. You're referring to something called tektites. We know of 4 classical, maybe by now 6 strewn fields of tektites. Those are distal impact ejectors, and not material that is found close to the impact. It's material that is formed probably from melting the upper surface of the impact area and then be ejected very far away. And impact modelers think that it needs a particular impact angle and velocity to create, and of course the right target. And this is why out of, say, 100 impacts, only 4 or 5 have produced these materials. In addition, glass is metastable and decays, so most of those glasses are just up to a few tens of millions years old. There's nothing 100 or 200 million years old, so that restricts it further.
Thank you.
Okay.
So,
Last. Sorry? Oh, sorry, there is a question online. So we are broadcasting across Africa via
Ooh.
the networks and
Okay,
stuff like
good.
that. So there's a question from Sue.
Can you comment based on statistics how many large impacts are missing from Earth's record?
I can't give a particular number. I would say about 90 to 99% are missing and have been eroded away.
But if it's large ones, then we're looking at 100 million years.
Well, large ones,
40,
but still,
40 plus.
I mean, we have,
We had a constant
how many
rate.
large ones do we have, you know? We have maybe, what do you mean by large? Larger than 50 kilometers or 10 kilometers or so?
Chicxulub.
Chicxulub size, well, I'm sure we're missing everything that is older than 2.5 billion years. So, and there have been dozens, if not hundreds, but there's nothing left. There's no surface left from that age.
Okay, Christian, as I said, let's
Okay.
call it quits now. But
Okay.
we've had people online from
Okay.
all over Africa. There's a network called Fast for Future that's EU funded. It's
Oh,
trying to build
great.
links through space and space science and research. So they've been online as well as various people as part of the different groups. Thanks to the physicists for coming over. Don't be strangers. We have interesting stuff here. And Christian, thanks very much for the talk, but particularly thanks for your ongoing leadership in these realms where we can do interesting stuff, but it also has relevance to it. So safe travels, and
Thank you.
also don't be a stranger.
Thank you.